How do we find magnetic flux? There's a formula for it. We use the flux symbol just like we had with electricity, but this time instead of putting a E at the bottom, we'll use B. This is magnetic flux now. And its formula is not E dot A, it's B dot A. Similar to electric flux though. All right, now we can see that the field here is coming in just parallel with the surface of the loop, which means that no magnetic field lines are actually cutting through the area of the loop. All right, so we can see that the flux is going to be 0 here. All right, now one way we can show that, though, would be to write in the B field, which is 1 Tesla in the I direction. Then we want to dot it with what's called the area vector. All right, so to get the area vector, we would just multiply the length times width. 0.3 meters times 0.2 meters. And then we have to give it a direction too. So the way we figure out the direction of the area vector is using that right-hand corkscrew rule. So imagine taking your fist and then curl your fingers around, okay, so that they're all curling this way in the direction of current through that loop, see? What'll happen is your thumb will point up. I'll try to use a dot to represent that. See, your thumb points up out of the page. It's pointing in the K-hat direction if we're using the conventional X, Y, and Z. So that's the direction I want to put on my area vector. If you dot an I with a K, though, the result is 0 because they're not parallel at all. They're totally perpendicular. Now we want to find any magnetic forces that are acting on the loop. So with this, you want to go around to each wire and use right-hand rule to figure out which wires will feel forces. So I'll start with number 1. Okay. With number 1, the current is in the opposite direction of B. Now we have a formula for force on a wire. The formula is force equals I times L crossed with B. It's kind of like QVB, okay? Very similar. V was the velocity of the particles, and here I is the current. L is going to be the length of the wire. The direction is going to be the direction of current. And then B is the field. As you can see, the direction of current and the direction of the field are 180 degrees opposite, which means that we will have no force on wire 1. By that same token, for wire 3, we're going to have no force. But we will have forces on wires 2 and 4. To figure out the direction of the forces, just point your finger, your pointer finger, in the direction of current, and then let your middle finger go in the direction of the B field. All right, I'll see if I can draw that here. Finger points this way. The middle finger points this way. Okay, so that's the pointer. This is the middle. And then what happens is the thumb points out of the page. These are just some other fingers there. All right, hope that makes sense. It is difficult to draw. So we're going to have a force. How much force? The force on wire 2 will equal the current, 4 amps, times the length of the wire, 0.3 meters, times the field strength, 1 Tesla. But the result is going to be in the positive k hat direction. That's important. You want to, give it a direction as well. I get 1.2 in the k hat direction. All right, now we should do the same thing on wire 4 though. You got to point your finger up this time. Okay, then have your middle finger point to the right in the B field direction. Okay, you'll get that. And this time your thumb is going to point down into the page. So what force do we have? We've got positive 1.2 k hat on wire 2. We're going to have negative 1.2 k hat on wire 4. This is going to make our loop want to spin. It's going to create a torque on the loop. So the area vector of the loop, we actually already kind of found that. It's just going to be the length times the width. And then you just have to give a direction to it, positive k hat. So 0.06 meters squared k hat looks like. Now let's find the magnetic moment for this loop. There's a formula for that as well. It's mu equals I times N times the area vector, where I stands for the current, of course. N is the number of turns in your loop. In our case, it's actually just 1 turn. And then you want your area vector. So it's 0.24. Okay, the units will be amps meters squared. And it's a vector as well. So the mu points out of the page. Lastly, we want to find the torque on the loop. Okay, so to get the torque, there's 2 ways we can do it. You can either use the formula that the net torque will be the sum of all the torques that are happening. Now this is from physics 1. We do R cross F for torque is one option. Now with magnetism, we have another option as well. So the other option is to use the formula torque equals mu crossed with B. Like that's what the magnetic moment is for. It's for finding the torque on an object due to the magnetic properties that it has. So we can actually try both methods. So for the old physics 1 way of doing it, all we'd have to know is the force that's acting. So you got this loop here. You got a force that's pulling up on the one wire and a force pulling down on the other wire. So this was 1.2 k hat, and this was negative 1.2 k hat. All right, so we know the forces. We just have to find this axis of rotation and then find the distances to the axis of rotation. So it's going to be 0.1 meters. So to get those torques, we just have to multiply 1.2 times 0.1. And we want to do that on the other side as well. All right, so it's a total of, looks like 0.24. So total torque the units will be Newton meters. And then we should come up with a direction for the torque as well. And this comes from physics 1 as well. So when an object wants to rotate clockwise, you would have said in physics 1 that that would be a negative torque. So you'd make it negative. But negative about what unit vector, right? So according to the directions given, this here would actually be the positive y direction. And this would be the negative y. Because I'm laying the loop down, on the table. So we would say then that this thing is rotating about the positive y direction in the normal way, which would be 0.24 Newton meters J. Yeah. Okay, it's rotating clockwise around the negative y axis. So it's like a double negative, if that makes sense. So this would be the right direction to give. And that's, that would be the final answer. So the other way of finding it, though, is just using this other formula. And you should get the same answer either way. So let's try it. Let's cross mu with B. I'll do it on the side here. All right. So I'm going to lay the loop down. I see that the mu is coming out of the page. It is 0.24 amp meters squared k hat. So that's out of the page. We see that the B field is coming in parallel to the loop. So these are the two things that we want to do the cross product on now. We want to do mu crossed with B. So use your right hand rule. Have your pointer finger point up. And then have your middle finger go to the right. So it kind of looks like this. And then there's some other fingers. When you do that though, your thumb points back in space. It points in this direction. So what does that mean? It means that that is the direction of torque. Okay, so this is the mu. We've got the B. Let's draw them all on the hand. This is the mu. This is the B. Okay. This is the pointer, by the way. This is the middle. And this one is the thumb. All right. Now if we just plug in our numbers, put in our mu, which was that, 0.24 amp meters squared. Put in our B field, 1 Tesla. And we determined the direction to be positive j hat according to the right-hand rule. So as you can see, they come out the same either way.